A short little tutorial on linear regression. So linear regression, super common in ecology. We use it all the time, and we all know a lot about it, but maybe haven't really thought about how it is actually done. So when we think of having a data set, we often have two variables. So we can call them x and y, and we can go out and measure a bunch of points that correspond to each other. So we might have a data set that looks something like this. And what we can do is we can turn that into a graph. We can plot that as a scatter plot where we have x and y and some kind of data. And so what we often want to do is see how x is related to y. And one of the ways we do that is by running a linear regression. And we've all seen this. We plot a line. Oh, not a great line. Plot a line through the data. And we know that the formula for this is y equals mx plus b, where m is the slope and b is the intercept. And you probably also run this in R. And so we can do that really easily using the lm function, where we say lm is y tilde related to x. We can run this as some kind of model fit, and we can look at the summary of our fit. And so if we look at that in R, we can do that using one of the built-in data sets. We can do something like the cars data set, where the cars data set gives us just the speed and distance, so sort of a two-variable data set. So we could do cars LM, linear model between distance and speed, and we can look at the summary of that. And what we can see is that R gives us the intercept and the slope. So in this case, if we look at the cars data set, we would know that y equals 3.9324, x minus 17.5791. So R does that for us super nicely. Also gives us p-value less than 0.05, so it's significant, and an adjusted R-square of 0.64. So how does this actually work? This is a model. We can implement it, but how is R actually calculating this? So there's the most common way, and the way that we're using here is called ordinary least squares regression. And what we're actually trying to do is sort of minimize these residuals between data points and the line of best fit. So let's just erase this. So again, if we have a scatter plot with a bunch of points and we draw a line through it, some of these points are going to be a lot closer to the line. And the closer those points are, the better our squared value is, the more related x is to y. And we can think of these as being what we call residuals, so the distance between the point and the line. And so each of one of these points has a unique distance. And the goal of ordinary least squares regression is to sort of minimize that residual error between the line of best fit and our data points. And so the goodness of fit, how we actually decide on the formula for that line, is by minimizing the sum of squared errors. And so each one of these errors can be thought of as the actual value y minus the fitted value, y hat. And if we take all of these, so they all have a unique y value, the sum of squares is equal to the sum of all of those residuals squared. And so our goal is to minimize that regression line. Our sum of squared errors, and we're trying to sort of minimize this value. And so given a collection of data, there is going to be some line, so some, y equals mx plus b that minimizes this sum of squared errors. And often you'll see this equation written as y equals b1 hat, where the parameters are sort of b1 and b0, x plus b0. And so these are sort of equivalent. There's just different mathematical notations of how to write that. And there's actually an analytical solution to this. This means there's actually equations that have been proven to be able to solve for b1 and b0. And those, if you just Wikipedia ordinary least squares regression, you can see that proof of how these are derived. And the equations for solving this are where b1 hat equals ssxy over ssxx, and b0 equals the mean of y minus b1 or the mean of x. And this is where ssxy equals the sum of xy minus sum of x times the sum of y over n. Oops. N. And ssxx equals the sum of x squared minus the sum of x squared over n. So we now have these equations that we can use to actually solve for b1 and b0. And we can do that in R. I mean, obviously, I just showed you that LM calculates this for you, but let's actually see how this works. So we can go back to R and start at the top here, where we're going to write a function to solve for b1 and b0 in our ordinary least squares regression line. So there's a few things we want to know. One of the things that we see in these equations is n, which is the number of data points we have. So we can just assign n to be the length of our data. So we're gonna have both x and y, and we're gonna actually just write this as a function. So we'll say that our linear coefficients are going to be a function of x and y. And we're going to put this all into a function where we can just sub in x and y data. So we're going to start off, we're going to say n is the length of x. This is going to be our sample size. And then let's calculate those statistics, SSXY and SSSX. So SSXY is going to equal the sum of x times y minus we're going to put these all in parentheses, the sum of x times the sum of y divided by n. And then SSXX equals the sum of x squared minus the sum of x squared divided by n. And so you can see how we've now translated these equations into our code. And it's actually pretty straightforward to do that. We then can find the actual coefficients, b1 and b0, where say B1 is Sx xy divided by SSSX. B0 is, let's see, the mean of y minus B1 times the mean of x. Now, functions in R can only return one object, so we're just going to combine these into a data frame and say our coefficients equal a data frame where the intercept is B0, or we can call that beta naught, and the slope is B1, beta 1. And then we're just going to tell our function to return coefficients. And let's see if this works. So we can save this as a function, and let's give it our cars data, because we've already used the cars data with our LM function. So let's do linear coefficients where x equals cars speed and y equals cars distance. And we come up with an intercept of minus 17.579 and a slope of 3.93. And if we look back at our summary from our cars, what we'll see is those are the same answers, which is great. We analytically solved for our linear regression model. And so you can see where R is really handy. It means you don't have to code all this math yourself, but now you can see that this math is doable. These equations might kind of look scary, but can be translated into R code fairly simply. So that's how we see what's sort of going on between LM. And obviously the LM function gives you a lot more sort of summary statistics, F statistics, R squared, p-values, and we could additionally code all of that ourselves if we wanted to. R is the analytical way of solving ordinary least squares regression. And that means that we actually have, equations that have been proved to solve for the two parameters in our model, B1 and B0. And we can then plug those in and get our full, model equation. So that is the way that, we have an analytical solution. So that means it's really fast. But in a lot of cases, if we're making models, we might not have those solutions, or maybe they don't exist. Maybe they're just would be really hard to derive. There's lots of reasons why those equations, we might not have those equations at hand when we have when we're trying to create models. And so the other way of solving for these parameters is to do so numerically, where basically it's kind of like a guess and check method where we just brute force our equations until we find the answer that works best. And this would be really time consuming for humans to do, because you would just have to keep subbing in different parameters for your slope and your intercept, trying to minimize your sum squared error. That would be painful. Good news is we have computers that are super computationally efficient and can do things in fractions of seconds that would take us a lot longer. So if we go back to our data, we remember that in ordinary least squares regression, we're trying to minimize, this equation. We're trying to minimize the sum of the squared errors. So what we can do is basically just keep subbing in parameters into our model. So keep subbing in different values for B1 and B0 until we find the best answers that minimize the sum of squared errors. And in modeling, we call that one thing we call that is optimization. We're trying to optimize these parameters to sort of best fit our line. And how that kind of works is that we could have some sort of axes where we have our parameter, and we do have two parameters in this model, but for the sake of this graph, we're just going to, let's say we're trying to find the best parameter for our slope. Let's say we fixed our intercept. And so we could just test out different values for our slope parameter. So we'll call this our slope. And this will be our sum of squared errors. And we can just pick a random value for the slope, see what the sum of squared errors is, pick another random value, see what its sum of squared errors is. And if this is decreasing, if our sum of squared errors is decreasing, that's good. If we pick another slope value, maybe it's a higher sum of squared errors. So, well, maybe we'll go back down here. And we keep guessing until we find some kind of minimum value where we have the slope parameter that is going to be our lowest sum of squared errors. And that's basically what computers do. They just keep testing different values, trying to find this minimum. We're trying to minimize that sum of squared errors. And this works really well, especially when we have linear relationships, because there's only one minimum. You can get into models where there might be some sort of other minimum, where you might get stuck in some other kind of valley, and that can lead to problems. But in this case, there's just one minimum. This won't be a problem trying to find it. So we can go back to R and actually set up a function to try and optimize sort of this numerical brute force method of just guessing what our parameters are. And so let's call this the sum of squared errors, where we're trying to minimize that. So our sum of squared errors is going to be a function of our parameters, as well as our data, so x and y. And we are going to have two parameters. We're going to have beta 1, which is going to be our first parameter. This is going to be a vector where we give it two parameters, and you're going to see why we're doing it this way in a sec. Beta 0, which is going to be parameter 2. And then we're going to fit our data with these parameters. And so we're going to say fitted is equal to beta 1 times x plus beta 0. And then we're actually going to find our sum of squared errors. So we're going to say SSE is the sum of our fitted minus y squared. So this equation here is just our, our sum of our squared errors, square the sum. And then we want our function to return SSE. So now we have a function, and we can test it. We can give it some parameters, where par equals, let's say, 5 and negative 10, x equals cars speed, y equals cars dist, and we can see that, it returns a value. If we change these parameters, it's going to change our SSE. And it would take us a long time to just keep on typing in different numbers and trying to minimize, get the lowest value of SSE. And so this is where the computational power of R comes in handy. We're going to use the optim function. You can look at the help file for optim and see that there are a number of different methods for general purpose optimization and different limits, constraints you can put in depending on your methods. Where the default is the Nelder-Mead, but there's also different methods which we might get into. And it gives you in the help file descriptions of these. So for instance, the BFGS method is a quasi-Newtonian method. And it tells us that Nelder-Mead, the default, works reasonably well, but is kind of slow. So let's give this a shot. We're going to say that our parameters, our starting parameters, are going to be, let's say, 5 and negative 10. And usually when you're doing optimization, you want to pick values that are realistic. If it's linear, the way we're doing it, it should optimize to the same values. But this is a situation where you could, if you had a nonlinear relationship, get stuck in other local minimum. Then we're going to say x equals, or we need to give it our function to minimize. So we're going to say function is SSE, x equals cars speed, and y equals cars dist. And so we can run this, and you can see it took less than a second, and our parameters are 3.93 and 7.57. And we can actually just call our parameters from our line. And if we actually went back and looked at our cars LM that we ran up here, you can see that what basically R did in this optim call was just iteratively check like a ton of parameters. Sort of, it seems instantaneous to us, but actually ran through a ton of parameters. And if we change these, we made these maybe 50 and negative 100, you can see it still ends up pretty close to being the same answer. And so if we made these really incorrect, we start getting values that don't make sense. And sometimes that's because the default number of guesses is low. Sometimes the method it's not as robust for checking. So in this case, we could try a different method. We could say method equals BF. Actually, let's look up what that was. We could try the Newtonian, the quasi-Newtonian, BFGS. Answers from our LM. So you can see in this case, this optimization brute force method worked well for coming up with slope and intercept parameters for our ordinary least squares regression, almost as well as the analytical solution. So if we didn't have the analytical solution, which we don't in many modeling applications, we can just use these optimum functions to try and just guess and repeatedly guess until we optimize our parameter values. And so that is sort of the numerical optimization routine for finding parameters.